Here are 3 photographs of the same object, taken from 3 slightly different places. And here is a 3D model built out of nothing but those 3 pictures. The machine that does that is called bundle adjustment, and it is the last step of essentially every reconstruction pipeline on Earth. But it can't do anything at all until you hand it one small function. About 20 lines of C++ that decide whether what you just saw comes out a building or a smear. Here is the one number those 20 lines exist to produce. This corner of the roof is somewhere real in space. 3 numbers, X, Y, and Z. Call it X, a 3 vector. A feature detector found that same corner in this photograph and said pixel 441, 309. 2 numbers, U across, V down. A 2 vector. That's the observation. It's measured. I don't get to argue with it. Now the other half. If I claim to know where the camera was standing, which way it was pointing, and what its lens does, I can work out which pixel that corner should have landed on. That's projecting it. 3 numbers in, 2 numbers out. A prediction. So, 2 dots for one corner. The one the detector measured, the one my model predicts. Subtract one from the other. Plus 7.3 across, and minus 0.4 down. 7.4 pixels of wrong. That gap is the reprojection error, measured in pixels, because it is a distance in an image. And note the order, predicted minus observed, the way the C++ writes it. 1 point, 1 photograph, 1 little arrow. Now do it for every point in every photograph. 3 cameras, 1,024 points, 3,072 arrows. Bundle adjustment grabs all the cameras and all the 3D points at once and shuffles them around until those arrows are collectively as short as they can possibly be. And the function we're about to read is the one that computes a single arrow. 1 point, 1 camera, 2 numbers out. It's called the SnavelyReprojectionError, and it is probably the most copy-pasted piece of code in 3-dimensional vision. So let's go and look at it. First, quickly where this thing sits, because we've been building up to it for a few videos now. A solver like Levenberg Marquardt wants exactly one thing from you. Not your data, not your pictures. It wants a residual function, something it can hand a guess to and get back a number saying how wrong that guess is. It squares those numbers, adds them all up, and rolls downhill until the total stops getting smaller. That's the entire relationship, which means the residual is the only thing the solver knows about your problem. Everything it believes about the world comes through that one function. Remember that. It matters enormously later in this series. In Ceres, you write it as a little C++ struct with an operator on it, a cost functor. And this one, SnavelyReprojectionError, is about 20 lines long. It's named after Noah Snavely, whose phototourism paper in 2006 built 3D models of landmarks out of tourist photographs scraped off the internet. Notre Dame, the Trevi Fountain, from strangers' holiday snaps. 3 years later, the same group did Rome, 150,000 photos of it in a day. And the file format they released? BAL, bundle adjustment in the large, is still the benchmark everybody tests against. This functor is the residual that goes with it. It ships inside Ceres, in the bundle adjustment example that everybody starts from. And from there, it has been pasted into research code, into theses, into things running in production this afternoon. Mostly, I'd guess, without being read very carefully. And look how little there is to read. Going in, 9 numbers describing the camera, and 3 describing the point. 12 numbers total. Coming out, 2. The gap in U and the gap in V. 12 in, 2 out. So the Jacobian of this thing, the matrix holding every output's sensitivity to every input, which is what the solver actually needs, is 2 rows by 12 columns per observation. We'll build that one properly a couple of videos from now. In this video, we're doing the anatomy, what those 9 numbers are, why there are 9 of them and not 11, and why the rotation is stored in the slightly strange way it is. 9 numbers per camera, 3 per point, 2 out. Start with the camera. 9 numbers, sitting in one flat array. Let's go through what each of them is actually for. The first 3 are the rotation. We call it omega, and it's a 3 vector, 3 doubles. Camera 0, camera 1, camera 2. Now, a rotation in 3D is normally a 3 by 3 matrix, 9 numbers. So how do we get away with 3? Because those 9 numbers aren't free. The columns have to be unit length and they have to be perpendicular to each other. Once you impose all that, there are only 3 genuine degrees of freedom left in a rotation. Roll, pitch, yaw. 3. So this is the honest minimal way to store one. It's called angle axis, and the trick is lovely. The direction of the vector is the axis you're spinning around, and its length is how far you spin, in radians. Concretely, omega equals naught, 0.26, naught. That vector points straight along y. So the axis is y, vertical, and its length is 0.26 radians, which is about 15 degrees. So turn 15 degrees about the vertical. That's a camera panning to the side. 3 numbers and you can read them. The next 3 are the translation, T, also a 3 vector, camera 3, camera 4, camera 5, where the camera sits, roughly. And I say roughly deliberately, because whether T is where the camera is or where the world is as seen from the camera is precisely the kind of convention that ruins an afternoon. We'll get to it. Then F, camera. A single number, the focal length. And note, 1 focal length, not 2. A normal calibration hands you fx and fy separately. This model has already decided that your pixels are square. For most sensors made in the last 20 years, that's true. It's still a decision and it was made for you. One thing that trips people up, f here is in pixels, not millimeters, which sounds like a category error the first time you meet it. Here's what it means. Say the lens is 4 millimeters and the sensor is 10 millimeters wide, split into 600 pixels. So 1 millimeter of sensor is 60 pixels. 4 millimeters times 60 is 240. F equals 240 pixels. It's the same physical lens measured in the units the image is actually made of. And then L1 and L2, camera and camera 8, 2 numbers. Radial distortion. That's the lens bending straight lines, the barrel look you get from a wide angle. In the little rig we'll be using all series, both of them are 0. It's a simulated camera and its lens is perfect. Real ones aren't, and the next video does that arithmetic properly. So 3 plus 3 plus 1 plus 2, 9, plus the point itself, x, another 3 vector. 12 numbers in total, and 2 come out. Now count what is not in that list. There is no principal point, no skew, no tangential distortion, no image width or height. 9 numbers, and a good half of what a calibration tool hands you is simply not here. And none of that is an oversight. Every absence is a deliberate decision. And every one of them pushes a job back onto you, into the data, before it ever reaches this function. Each one is also a place where a reconstruction can go quietly and catastrophically wrong. And there's a whole video coming on exactly that. For now, notice that the gaps are deliberate. Last thing, about the shape of it. It's a flat array. 9 contiguous doubles for the camera, 3 contiguous doubles for the point, and Ceres hands your function a raw pointer to each one. 2 blocks, not 1 block of 12. And that split isn't cosmetic. This residual touches exactly 1 camera and exactly 1 point out of maybe 500 cameras and 100,000 points. Every other parameter in the problem gets a derivative of 0. Hold on to that. It's the reason the Jacobian of a real reconstruction is almost entirely zeros. And that is a whole video of its own.